Today we're going to talk about nonlinear autonomous systems of differential equations, first-order differential equations. Nonlinear means that the independent variable is t, say time. The dot is like Newtonian notation for the derivative. So it's the derivative with respect to time. So x dot is the same as the derivative of x with respect to the independent variable t. And y dot is the derivative of y with respect to t. So nonlinear means that the right-hand side functions are not linear functions in x and y. Autonomous means that the right-hand sides are independent of time, are independent of the time, independent variable. So what we want to do is look at the equilibrium points for these systems. Equilibrium points are x-y pairs, which make the first-order derivatives with respect to t 0. So this means we need p at the equilibrium point to evaluate to 0, so that x prime is 0. And then likewise, q at the equilibrium point should be 0, so that the derivative of y with respect to t is 0. So once we identify the equilibrium points by solving a system of equations, we then want to classify the equilibrium points. And the classification of the equilibrium points is based on a linearization centered at the equilibrium points. And in that case, so at that point, it's this matrix. We take the partial derivative of p with respect to x and y, and q with respect to x and y, and evaluate at the equilibrium points. The classification of the equilibrium points is based on the eigenvalues of that matrix. And so the eigenvalues are going to be called R1 and R2. And from this table that we can look at the type of equilibrium point, and then classify it as stable, asymptotically stable, or unstable. Stable just means that if you start at a position close to an equilibrium point, you stay close to it. Asymptotically stable means that, yeah, you're a stable equilibrium, but also you have that in the long run as t goes to infinity, and as long as you start sufficiently close to the equilibrium point, at the limit as t goes to infinity, you go to that equilibrium point. Otherwise, you just say we have unstable equilibrium point. But again, these will be determined by the eigenvalues of this matrix. So we can look at an example. So this system is autonomous, x times y squared. So that term is not linear in y. First of all, you want to find equilibrium points. So this is like the right-hand side here is your function p of x and y, and the right-hand side is q of x and y. Finding the equilibrium points is to find where these are simultaneously 0. So we're going to set the right-hand sides equal to 0 and try to solve that system. The algebra you do here is situational. Here it's not that bad. Looking at the second equation, we see that x is 3 times y. Then we can substitute for x, say, into the first equation. 2 times x becomes 2 times 3y minus 3y minus x, that's 3y, times y squared. So we get 3y minus 3y cubed. So we see that y could be 0, y could be 1, or negative 1. That means that x is either 0, 3, or negative 3. So we get 3 equilibrium points. So next we're going to classify what happens, we're going to classify these 3 equilibrium points. So towards that end, we're going to compute this matrix, which is the derivative of p with respect to x, derivative of p with respect to y, derivative of q with respect to x, derivative of q with respect to y. We're going to evaluate at each equilibrium point and compute eigenvalues there. Remind ourselves of the system. So now we're going to create our matrix. We're going to differentiate p with respect to x and y, then differentiate q with respect to x, then with respect to y. So now we can start listing our equilibrium points. So at the equilibrium point 0, 0, our matrix becomes 2, 0, 1, negative 3. And so we're going to compute the eigenvalues. So remember that's solution to the characteristic polynomial set equal to 0. So you're probably aware that since this is a triangular matrix, the eigenvalues are just going to be the diagonal entries themselves. The equilibrium of 0, 0, you get two eigenvalues. One positive, one negative, both are real numbers. One is positive and one negative, both are real. So for the previous problems we had, the linear systems, that was an unstable saddle, and it's still an unstable saddle for our nonlinear system. So we're going to look at our matrix at the next equilibrium point, 3, 1. So evaluating, we get 1, negative 9, 1, and negative 3. And we want to find the eigenvalues by finding the roots of the characteristic polynomial. So we see that this time, after using the quadratic formula, the eigenvalues are complex. Notice that the real parts are negative. So let's go back to our table to classify what happens at our equilibrium point. Well, if you recall from the linear systems, if we had complex conjugates, then we know we had a spiral, and if the real part was negative, then we know we had a asymptotically stable spiral. Roots are complex conjugates, the real part is negative, so we get a spiral, and it's asymptotically stable. The equilibrium point 3, 1 is a asymptotically stable spiral, in fact. And it turns out that if you were to use the next critical or equilibrium point, you would also get a asymptotically stable spiral. You get exactly the same eigenvalues. So now we're going to look at another example. We have an autonomous system of first-order differential equations. The right-hand side is independent of time, t, and it's nonlinear in x nor y. To find the equilibrium points, we're going to set x dot and y dot equal to 0 simultaneously. We can take advantage of the fact that x times these are common terms. If we multiply both sides of the first equation by positive 3 and add the two equations, x times y terms would cancel. They would add to 0. So it looks like we get a relationship between x and y here. So we see that that leads to two cases. Case 1 is that y just could be equal to 3x. Now let's see if that gives us anything. I say looking at the first equation. We have from the first equation we have 3 minus 6x squared plus 2 times x times y, where y is 6x. So we get that 3 equals 0. So this is, of course, a contradiction. Okay, so case 1 wasn't fruitful. Case 2, so y could be negative 3 times x. Again, looking at the first equation, we can replace y with minus 3x. So x plus or minus 1/2. Then from the equation, we know y says that y is negative 3 times x. You see the critical points are 1/2, negative 3/2, and negative 1/2 and positive 3/2. So these are our equilibrium points. So now we want to classify those equilibrium points. For that, we're going to need to use our second matrix, or 2x2 matrix of derivatives. Find the derivative of p with respect to x and y. And then we're going to evaluate these at our critical points. We need to compute the eigenvalues of this matrix at these two equilibrium points. We want to find the roots of the characteristic polynomial. So here the eigenvalues are both real and positive. So this means that we have an unstable equilibrium. Likewise, for the other equilibrium point, we compute the roots of the characteristic polynomial. So here both roots are real and negative. So we have a asymptotically stable equilibrium. So let's make sure we got that right in the first case. Both eigenvalues were positive. So we had an unstable, I should have said node as well. And for the second equilibrium point, we got two negative real eigenvalues. So that's a asymptotically stable, I should have said node. Now we're going to look at models of pairs of species that might have to share resources, fight over resources, fight with each other. So here x and y might represent the population size of a certain species, say species X and species Y. So this would give you how many species you have of each type at time t. The relationship can be modeled by some family of differential equations. The name slips my name. One of the names is Volterra. So here's an example. So as always, we want to find equilibriums by setting the rate of change of the growth of each species to 0. That is to say, we want to set these right-hand sides equal to 0. We can do the case where from the first equation, x could be 0. And then you have the subcases where and from the second equation, y might be 0 or y might not be 0. If x and y are both 0, that definitely satisfies both equations. So that's the equilibrium point. I guess that makes sense. But if x and y represent population sizes, then if they're 0, then there should be no change in population sizes, no birth, no deaths. But if x is 0 and y is not, then from the second equation, we see that instead of writing 2x, I can write 0 there, because this is the case where x is 0. So you see that y would have to be 4. So that's another critical point, 0, 4. So now we can go back to equation, we can do the case where x is not 0. If y is 0, well then you can go to the first equation and get where y is 0. So this means that x has to be 3. So 3, 0 is an equilibrium point. Now if both x and y are non-zero, then we actually have to look at both equations and we see that must be then 0 and this must be 0 at the same time. So you have a system of two equations to know. X would be 1 and y would be 2. So the 4 equilibrium points are 0, 0, 0, 4, 3, 0, and 1, 2. Let's classify what happens, what kind of equilibrium points these are, and let's interpret it in terms of populations for the two species. So I slightly rearranged the right-hand sides of our system, and now we need to find the matrix. Consists of the derivatives of p with respect to x and y and q with respect to x and y. We're going to take this matrix and evaluate it at each of the 4 equilibrium points. So at the origin, we get the matrix has 2 positive eigenvalues. So that's going to be an unstable node. So next, at 0, 4, we get 2 negative eigenvalues. So that's an asymptotically stable node. At equilibrium point, 3, 0, again, we get 2 negative eigenvalues. That's another asymptotically stable node. So finally so it looks like we get 2 real roots, one of which is negative and the other of which is positive. So that's a saddle, unstable saddle. So now let's look at phase portrait of the two populations. And imagine that these 4 equilibrium points in some way cut up the first quadrant. So only feasible region for x and y, since their population sizes are where x and y are both non-negative. The origin was unstable node. Equilibrium point 1, 2 was saddle. 3, 0 was stable node, or asymptotically stable. So depending on what the initial sizes of the populations are, say you would be moving away from this unstable node. And if you would approach the saddle, but by the nature of a saddle, you would swerve away from it and go towards the stable node. Likewise, if you start somewhere over here instead, similar trajectory. This time you would end up at the other stable node. There would be some trajectories here where you approach the saddle. So suppose you start off in this first kind of quadrant. In your trajectories, you would move away from the origin because it's an unstable node. You would move towards that stable node. So this is a scenario where population species Y started out sufficiently larger than X, that X died off, right? Because the population size for X went to 0. So it looks like this would be a competitive species X and Y would be competitors. Similarly, if you were to start, let's say, in this quadrant over here, species X wins out. So species X was sufficiently large population. Eventually, it would make species Y die out because here species Y goes to 0. On the other hand, if you started somewhere else, similar ideas, right, you'd still end up with one of the species dying out. So these are definitely competitors. They can't coexist. Regardless of where you start, one of them will die off. Okay, so now we have an example where we have 2 species that can coexist. We're going to find equilibrium points first. Equilibrium points are where the first derivatives are equal to 0 simultaneously. We set the derivatives equal to 0 and solve the system. So the equilibrium points are, well, both x and y could be 0. X could be 0, in which case, so suppose x is 0 but y is not, in which case we get 0 and 4/3. On the other hand, if y is 0 but x is not, then x has to be 2. Finally, suppose that neither x nor y are 0, in which case these two factors have to be 0, which gives us a system of equations where we can easily see that y would be 1, and if y is 1, we see that x has to be 1. So we have 4 equilibrium points. Next, we want to compute this matrix of derivatives so as to be able to classify the equilibrium points as stable or unstable. Derivative of p with respect to x, derivative of p with respect to y, derivative of q with respect to x, derivative of q with respect to y. So now we're ready to evaluate our matrix at the critical points and find the eigenvalues so as to classify the equilibrium points. At the equilibrium point at the origin, you see that our matrix is a diagonal matrix, and the eigenvalues of a diagonal matrix are just the diagonal entries. So the eigenvalues are 4 and 4. So that's positive and real, so that's an unstable equilibrium. Looking at our chart, we see that the roots are repeated, real and positive. So we have either a node or a spiral, but here the important thing is that it's an unstable equilibrium. Next, we evaluate our matrix at the equilibrium point 0, 4/3. We see that we get a triangular matrix, so the eigenvalues are just the diagonal entries. So we have an eigenvalue of 4/3 and -4. So we have real eigenvalues where one is positive and one is negative. So that's a saddle point, inherently unstable. So indeed, we check our chart. We have one negative and one positive real root, so that's a saddle, and it's unstable. Our next equilibrium point is 2, 0. Evaluating our matrix there, we get another diagonal matrix, so the eigenvalues are just the diagonal entries. We see the eigenvalues are real but opposite in sign, so we have yet another saddle. And we look at our final equilibrium point, 1, 1. Evaluating our matrix there, we get a matrix which is not triangular, so we will go ahead and compute the characteristic polynomial and set it equal to 0 in order to solve for the eigenvalues of this matrix. Computing the determinant of our matrix minus r times identity, we get a polynomial that factors nicely. We set that equal to 0, and we find that the two roots are negative, the real and negative. So this means that we have an asymptotically stable node. Checking our chart once again, we see that two negative real roots indicates a node that's asymptotically stable. So finally, we're going to sketch a phase portrait so we can qualify what's going on at these equilibrium points. We plot our 4 equilibrium points. Of course, this is all happening in the first quadrant of the xy plane, since x and y represent population sizes of species. We can sketch guiding lines and note that the origin is unstable node or spiral. These two equilibriums on the axes are saddles, and then this is a stable node. So if we had a trajectory of some sort, it would, let's say if we start over here, it would move away from the unstable node at the origin and then fly by the saddle and go towards the stable equilibrium at 1, 1. So likewise, so starting over here somewhere, we would have a trajectory going towards the stable node. So what this is telling us is that at point 1, 1, the species could coexist, in fact, in equal numbers, I guess, since x and y are both 1. So that was an example of a model of two species that could coexist because we have a stable node at the equilibrium where neither x and y are 0.